Welcome future certified energy managers. This video is all about electric motors, a key area in energy management due to their widespread use and significant energy consumption in industrial settings and beyond. To truly understand how to manage their energy effectively, we first need to grasp some fundamental electrical and mechanical principles. So let's jump in. In order to understand electric motors, we need to be fully aware about the basic understanding of electrical circuits. We will start by Ohm's law. Ohm's law describes the relationship between voltage, current, and resistance in an electrical circuit. Voltage V is the electric potential difference, current I is the flow of electric charge, resistance R opposes this flow. Simply put, Ohm's law tells us how much voltage is required to drive a specific current through a given resistance. Next, let's look at Kirchhoff's law, which are essential for analyzing more complex circuits. Kirchhoff's current law, or KCL, focuses on where currents meet. Imagine a junction, a point where multiple wires connect. KCL states that the total current flowing into that junction must equal the total current flowing out of it. It's all about the conservation of electric charge. Charge cannot just disappear or appear at a connection point. The sum of the currents entering equals the sum of the currents leaving. Next, we have Kirchhoff's voltage law, or KVL. This law looks at closed loops within a circuit. KVL states that if you trace a path all the way around any closed loop in a circuit, adding up all the voltage increases, like from a battery, and all of the voltage drops across resistors, the total must equal zero. This is based on the conservation of energy. The energy provided by the sources must be used up by the components in the loop. The sum of all electrical potential differences around any closed loop is zero. So, Ohm's law tells us about how individual components, while Kirchhoff's law help us analyze how these components interact within a complete circuit. They are fundamental tools for understanding and designing electrical systems. Now, let's talk about the two main types of electrical current you will encounter, DC and AC. DC stands for direct current. Think of it as a one-way street for electricity. In DC circuits, the electric current flows consistently in only one direction. A common example of DC source is a battery. The positive and negative terminals of a battery maintain a constant polarity, ensuring the current always moves from one way to the other. In contrast, we have AC, which stands for alternating current. Imagine this as two-way street with traffic changing direction regularly. In AC circuits, the direction of the electric current reverses periodically. The power supplied by electric utilities to our homes and businesses is typically AC. This constant change in direction is usually represented by a smooth wave pattern. So, the key difference is the direction of flow. DC flows steadily in one direction, while AC constantly switches direction. Both are incredibly important and used in countless applications around us. Now, let's explore a fundamental principle connecting magnetism and electricity, Faraday's law of induction. This law explains how a changing magnetic field can actually create an electric current in a conductor. It's like magic, but it's pure science. Faraday discovered that it's not enough to just have a magnetic field. The field needs to be changing in strength or direction relative to the conductor to induce this electrical effect. This push that causes the electric current to flow is called the induced electromotive force, or EMF. While it's related to voltage, it's specifically the voltage created by this changing magnetic field. Faraday's law states that the induced EMF in any closed circuit is directly proportional to the rate of change of the magnetic flux through that circuit. E represents the induced EMF, the voltage created. Delta phi represents the rate at which the magnetic flux is changing over time, T. The negative signs indicates the direction of the induced current, a concept related to Lenz's law, which opposes the change in magnetic flux. Think of magnetic flux as the amount of magnetic field lines passing through a loop of the conductor. If this number of lines changes, perhaps by moving a magnet, changing the strength of a magnetic field, or altering the orientation of the loop, Faraday's law tells us that an EMF and thus a current will be induced in the conductor. The faster the change in the magnetic field, the greater the induced voltage. Faraday's law of induction is the cornerstone of many technologies we use every day, from electric generators that powers our cities to transformers that regulate voltage and even wireless charging. It's a beautiful demonstration of the interconnectedness of electricity and magnetism. Building upon Faraday's law, we have Lenz's law, which tells us about the direction of that induced current we just learned about. Lenz's law states that the induced current will flow in a very specific way. It will create its own magnetic field that opposes the change in magnetic flux that originally caused that current. Think of it like this. Nature doesn't like change. When a changing magnetic field tries to induce a current, the resulting current acts to counteract that change. If the magnetic field is increasing through a loop, the induced current will create a magnetic field pointing in the opposite direction to try and reduce the increase. If the magnetic field is decreasing, the induced current will create a field in the same direction to try and maintain it. Remember that negative sign in Faraday's law? That negative sign is a direct consequence of Lenz's law, mathematically indicating this opposing direction of the induced EMF and current. This opposition isn't just a Kirchhoff rule, it's a fundamental consequence of the conservation of energy. If the induced current flowed in a direction that reinforced the change in magnetic flux, it would create a positive feedback loop, leading to an ever-increasing current and energy without any external input, which would violate the laws of physics. Lenz's law ensures that energy is conserved. The induced current requires work to be done against its opposing magnetic field. So, Faraday's law tells us how much volt is induced by a changing magnetic field. Lenz's law tells us the direction of the resulting current, always acting to resist the change that produced it. Together, they provide a complete picture of electromagnetic induction. Now, let's delve into the concept of a magnetic field, which is crucial for understanding phenomena like Faraday's law. A magnetic field is essentially an invisible region of force that's created by either moving electric charges or by magnets themselves. This field has the ability to exert forces on other moving electrical charges or on materials that are magnetic, like iron. Think of it as an area of influence where magnetic effects can be felt. Interestingly, a magnetic field isn't just produced by permanent magnets. where an electric current flows through a conductor. It also generates a magnetic field around that conductor. The shape of that magnetic field around a straight wire carrying current is that of a concentric circles centered on the wire. Imagine making a series of rings around the wire. Those represents the magnetic field lines. There is a handy way to figure out the direction of these circular magnetic field lines. It's called the right-hand rule. To use it, imagine grasping the wire with your right hand, with your thumb pointing in the direction of the conventional current, which is the direction positive charge would flow. Then the direction your fingers naturally curl around the wire indicates the direction of the magnetic field lines. So, to recap, magnetic fields are created by moving charges or magnets, and they exert forces on other moving charges or magnetic materials. Specifically, a current flowing through a wire produces a circular magnetic field around it, and we can use the right-hand rule to determine its direction. This understanding of magnetic field is fundamental to grasping how devices like motors, generators, and transformers work. Let's shift gears and talk about something that makes things spin: torque. Torque is essentially a measure of how much a force can cause an object to rotate around a specific axis. It is the rotational equivalent of linear force. While a regular force makes things move in a straight line, torque makes things turn. Imagine using a wrench to tighten a bolt. The force you apply to the handle of the wrench creates a torque that causes the bolt to rotate. The amount of torque generated depends on several factors, and it's calculated using this formula. T equals F multiplied by R multiplied by sin theta. Let's break down each part of this equation. F represents the force you apply. The stronger the force, the greater the potential for rotation. R is the distance from the axis of rotation to the point where the force is applied. This distance is often referred to as the lever arm. Think about it as the wrench again. Applying force further down the handle makes it easier to turn the bolt. Theta is the angle between the force vector and the lever arm vector. The torque is maximum when the force is applied perpendicular to the lever arm at a 90-degree angle, where sin 90 degree is equal to 1. If you push directly along the lever arm at 0 or 180 degree, you won't get any rotation. Consider opening a door. The hinges are the axis of rotation. The force you apply to the handle creates a torque around those hinges, causing the door to swing open. The further you push from the hinges and the more you push perpendicular to the door, the easier it to open. Torque is a fundamental concept in physics and engineering, crucial for understanding anything that involves rotation, from simple levers and gears to complex motors and turbines. It is the twisting force that makes the world go around, literally. Let's move on to a more familiar concept: speed. In simple terms, speed tells us how quickly an object is moving. It's defined as the distance traveled by the object per unit of time. Imagine a car traveling down a road. The speed of the car tells us how many meters or kilometers it covers in 1 second, 1 minute, or 1 hour. We can calculate using a straightforward formula. Speed equals distance divided by time. As you can see, speed is what we want to find out. Distance is the total length the object has traveled. Time is the duration it took to cover that distance. It's important to note that speed is a scalar quantity, meaning it only has magnitude. a numerical value and doesn't have a direction. If we want to describe both the speed and the direction of an object's motion, we use the term velocity. Understanding speed is fundamental to describing motion in physics and everyday life. It allows us to quantify how fast things are moving and to make predictions about their movement. Finally, let's discuss power, a crucial concept in both mechanical and electrical systems. Power is defined as the rate at which work is done or the rate at which energy is transferred. It tells us how quickly energy is being used or converted. Think about it as light bulb. It powers ratings tell us how much electrical energy it consumes per second to produce light and heat. In mechanical systems, power can be calculated in a couple ways. P equals work divided by time. One way is as the work done divided by the time it takes to do that work. So if you do the same amount of work faster, you are using more power. Or P equals F multiplies by V. Another way to calculate power in mechanical systems is by multiplying the force F applied to an object by its velocity, V. This makes sense because a larger force moving an object at a higher speed requires a greater rate of energy transfer. In electrical systems, power is also a key quantity, and it can be calculated using the following formula. P equals V multiplies by I. Here, P, power, is equal to the voltage V across a component multiplied by the current I flowing through it. Consider an appliance plugged into an outlet. The power it consumes depends on both the voltage of the electricity supply and the amount of current it draws. A higher voltage or a higher current or both means this appliance is using more electrical power. The standard unit of power in the International Systems of Units, SI, is the watt, W. 1 watt is equals to 1 joule of energy transferred or work done per second. Understanding power is crucial for analyzing energy consumption and efficiency in various systems, whether they are mechanical or electrical. It tells us not just how much energy is involved, but also how quickly that energy is being used or transferred. That wraps our discussion about the essential electrical and mechanical principles behind motors. In our next video, we will uncover why motors are so vital and the incredible range of motor types out there. Please make sure you stick around for that to get the full picture and explore the fundamentals of energy and its uses. Our previous videos are a must watch. Subscribe now so you don't miss any future explorations.